In this module, we will consider standing waves. Standing waves are a phenomenon in which propagating waves appear to stop traveling. In reality, standing waves are a result of the superposition of harmonic waves traveling in different directions. The simplest examples are of superposing sinusoidal waves traveling in opposite directions in one dimension, but standing waves can occur in higher dimensional objects. Consider two sinusoidal waves with the same frequency traveling in opposite directions on a string. The two individual waves are y1 equal to a sine kx minus omega t, so this is a wave traveling to the right, and y2 equal to a sine kx plus omega t, which is a wave traveling to the left. Now consider their superposition. We use the usual simplification for adding two sine functions together, and simplifying, we find that the final result appears in the form in which each point on the string behaves like a simple harmonic oscillator. All points on the string oscillate with the same frequency omega, as shown by the term cosine omega t, but multiplying this is an amplitude, which is different for each point along the string. In this case, the amplitude is given by 2a sine of kx. Now consider an animation of the standing wave. There are certain locations along the standing wave where the amplitude of the oscillations vanish. These points are called oscillation nodes. While nodes never move, the remainder of the string oscillates with the frequency omega. We see that the distance between two nodes is 1/2 the wavelength of the standing wave. Halfway between each pair of nodes is an oscillation antinode where the standing wave has its greatest amplitude. Each pair of antinodes is also separated by a distance of 1/2 the wavelength of the standing wave, and nodes and antinodes are separated by 1/4 of the wavelength of the standing wave. If you have the two ends of a stretched string constrained so that they cannot move, then the string will tend to oscillate at whatever frequencies allow nodes to exist at both ends. This means that the length of the string between the fixed ends must be an integer number of half wavelengths. In this case, there are 3 half wavelengths along the length L. In general, the length is divided into n half wavelengths. And if we use the fact that the product of the wavelength and the frequency is the speed of the wave, which we can write in terms of the tension and mass per unit length of the string, we obtain a pair of equations that are useful for relating the set of possible oscillation frequencies for a string of length L to the tension and mass per length of the string. The set of possible oscillation frequencies is called a harmonic series. The lowest frequency, F1, is called the fundamental frequency, while the nth frequency is called the nth harmonic. When standing waves are present in a column of air, we must carefully consider the conditions that are present at the two ends of the air column. Unlike waves on a string, we can consider the oscillations either in terms of displacement of the air or as changes in the air pressure. These two descriptions of air waves are 90 degrees out of phase, meaning that nodes in one description correspond to antinodes in the other. Let's consider two examples of standing waves in a column of air. The first is a pipe with the right end open. Actually, both ends of the pipe are considered to be open. Air is blown into the left end of the pipe, and its motion past a block causes turbulence and oscillations that create a standing wave down the pipe of length L. But the opening near the block means that this end of the pipe is open and both ends will remain at atmospheric pressure, meaning that pressure nodes are present at both ends of the pipe. We can also view this as having displacement antinodes at both ends of the pipe. The standing waves in the pipe can be viewed either as pressure waves or as displacement waves. The fundamental mode will have 1/2 wavelength between the two ends of the pipe, with either pressure nodes at both ends or displacement antinodes at both ends. The second harmonic will simply add an additional 1/2 wavelength within the length of the pipe, and each higher harmonic will add an additional 1/2 wavelength. Finally, we summarize some formulas that are useful in considering standing waves in a column of air where both ends of the column are open. In this second example, the right end of the pipe is closed. The left end of the pipe is as in the first example, with air blown in to set up oscillations down the length of the pipe. But the closed right end of the pipe means that this end of the pipe will now have a pressure antinode or a displacement node. The standing waves in the pipe can again be viewed either as pressure waves or as displacement waves. The fundamental mode will have 1/4 wavelength between the two ends of the pipe because one end of the pipe must be a node and the other an antinode. The second harmonic will again simply add an additional 1/2 wavelength within the length of the pipe. And each higher harmonic will also add an additional 1/2 wavelength. Again, we summarize some useful formulas for understanding standing waves in a column of air with one end open and one end closed. The formulas are slightly more complicated because each harmonic must include the 1/4 wavelength needed for the opposing conditions at the two ends of the pipe.